Okay, the next talk is presented by Wei Dong on document hashing with mixture prior generative models.
Good afternoon. I'm Wei Dong from Shanghai University, and I'm a presenter today. A little bit of background about the problem that we are looking at here. We are trying to do the task of similarity search, which aims to find items that look most similar to the current one from a huge amount of data and are found in extensive applications like plagiarism analysis and collaborative filtering, etc. One strategy to do this task is to represent each document as a continuous representations. And with continuous representations, the Euclidean distance and cosine similarities are usually employed to measure text similarity between documents. But this can be very computation expensive. Semantic hashing is an effective way to accelerate the searching process by representing every document with a compact binary code. In this way, one only needs to evaluate the Hamming distance between binary codes. There are some motivations of our work. First is existing semantic hashing methods usually require two-step chaining, which is then a continuous representation for the document first, and then use a separate step to casting the continuous representations into binary code after chaining process. But this kind of two-step chaining may result, this model is prone to get stuck at poor performance. And second is that only the simplest priors are used in existing generative hashing models, and it is widely known that the priors play an important role on the performance of generative models. Let's study some preliminaries on the generative semantic hashing. Let X and Z denote input document and its corresponding latent representation, respectively. Existing generative hashing approaches model a document with a joint probability density function Px and Z, which is equal to P theta X condition on Z times Pz, where P theta X condition on Z is the decoder and Pz is the prior, and the binary code of each document is obtained from its corresponding latent representation Z. And the different Pz leading to different models. For example, in VDSH, the prior Pz is a Gaussian distribution, so this model requires two-step chaining since the latent representations is also subject to a Gaussian distribution. Nash replaced the Gaussian prior by a Bernoulli distribution, so the document can be cast into binary code in an end-to-end manner in these models. It is widely known that the generative model with better modeling capability often implies the obtained latent representations are also more informative. So to increase the modeling ability of Px and Z, we may resort to more complex decoder, P theta X condition on Z, for example, LSTM or CNN. And the second is to use more expressive priors. However, as in Nash, employing expressive decoder likely destroying the distance keeping property, which is essential to yield good hashing code. So in this paper, instead of employing a more complex decoder, mixture prior were leveraged to address this issue. We first replaced the prior by the following Gaussian mixture prior, and which can be written as equation 2. And where k is the number of mixture component and pi k is the probability of choosing the k's component. Thus, the document X is modeled as Px, Z, and Z, which equal to P theta X condition on Z times P Z given C times PC. And here, P Z condition on Z is subject to a Gaussian distribution, and PC is subject to a categorical distribution. And we call this model as GMSH. And to train this model, we seek to optimize the lower bound of log likelihood, which can be written as equation 4. And the approximate posterior distribution Q phi Z condition on X is restricted to take the form of Gaussian distribution, which is also continuous. Thus, a separate step is still needed to cast the continuous representations into binary code. So to avoid the separate casting step used in GMSH, we further propose to replace the prior by the following Bernoulli mixture prior. And we call this model as BMSH. And similar to GMSH, this model can be trained by maximizing the variational lower bound, and which maintains the same form as equation 4. And at this time, the approximate posterior distribution Q phi Z condition on X is restricted to take the form of Bernoulli distribution, so which yields binary code directly. However, due to the Bernoulli assumption for the posterior, the commonly used reparameterization trick for Gaussian distribution cannot be used to directly estimate the first term in equation 4. Fortunately, we can parameterize the ith element of binary sample Z from Q phi Z condition on X as equation 6. And here we can see that G phi X is the output of the encoder. This reparameterization method used above can guarantee generating binary samples. However, backpropagation cannot be used to optimize the lower bound, since the gradient of sine function with respect to its input is 0 almost everywhere. To address this problem, the stress-through estimator is employed to estimate the gradient for the binary random variables, where the derivative of Zi with respect to phi is simply approximate by this term. And thus the gradient can be backpropagated through discrete variables. When label information is available, it can be further leveraged to learn a more expressive binary code, since label provides extra information about the similarity between documents. Specifically, a mapping from the latent representation Z to the corresponding label Y is learned for each document. And taking the supervised objective into account, the total loss is defined as equation 7. And we have a parameter alpha to control the relative weight of the two losses. About the experiment, there are three public benchmark datasets are used in our experiment, and their names are Reuters, 20 news groups, and TMC, which is an air traffic report provided by NASA. And the TF-IDF feature of a document is used as the input of the encoder. We employed the retrieval precision as the evaluation metric, which is the percentage of document among the top 100 retrieved ones that sharing the same label with the query document. And the retrieval precision under the case is of 16, 32, 64, and 128 bit hashing code are evaluated respectively. And the component number K and the parameter alpha in equation 7 are determined based on the validation set. There are two cases that we have discussed. First is that the position of the top 100 retrieved documents on Reuters datasets in unsupervised setting. And we compared our poster model GMSH and BMSH with several benchmark, very strong baseline, and Nash is a kind of out-of-state model before our works. And as we can see from this table, our GMSH outperformed previous model constantly, which strongly demonstrates the benefit of using mixture prior on the task of semantic hashing. And one explanation is that mixture prior allowed the document to be regularized by different mixture components, guiding the model to then a more distinguishable representation for the document. And it can be further observed that BMSH achieved the best performance. And it may be because that the proposed Bernoulli mixture prior, which takes the advantage of both mixture prior and the end-to-end chaining, thus is more suitable for the task of hashing. And a similar result can be seen in a supervised case, suggesting that the proposed mixture prior can be also extended to the supervised hashing. To investigate the impact of the component number K, experiments are conducted on GMSH and BMSH under different component number K on different datasets. And this table shows the precision of top 100 retrieved documents with different number. And as we can see from this table, as long as the number K is not too small, the performance loss is still acceptable. And for the BMS model, the performance is stable across all considered datasets and K values. In summary, in this paper, deep generative model with mixture prior were proposed for the task of semantic hashing. And we first proposed to use a Gaussian mixture prior to produce high-quality hashing codes. To avoid the separate casting step used in GMSH, we further proposed to use Bernoulli mixture, which offers the advantage of both mixture prior and the end-to-end chaining. And the experimental result indicates that the proposed model using mixture prior outperforms existing models by a substantial margin. Thanks for your attention, and do you have any questions?
Hello, yeah, thanks for a nice talk. So I have a question regarding, so the state-of-the-art baseline in your unsupervised experiments is also supervised in the paper. You use Nash, but in the unsupervised you use like the simplest, most simple version of Nash. They have 3 versions each, more advanced than the next, but they all work in unsupervised settings. So if you use the full version, you are 2 out of 3 experiments are actually below state-of-the-art in performance. Is there a reason you used that version of Nash and not the complete version?
Thank you for your questions. And in the supervised case, we compared with several benchmarks and VDSH and Nash, which is also which are both VDSH and Nash are generative semantic hashing, and they also can be extended to semantic hashing, or extended to supervised semantic hashing.
Yes, but I mean specifically in the unsupervised case, your results are below state-of-the-art because you compare to the one version of Nash and not the complete model.
Sorry, I cannot hear you.
We can talk afterwards.
Thank you, thank you.
We have maybe time for one more question. Okay, no, let's move on. All right, let's thank the speaker again.